quantum Darwinism is basically it's a way how it's basically like Darwinian evolution.
Yeah.
So there are certain quantum states that survive this transition of becoming classical, and these are called pointer states. So what is a state? A state is all of this is very difficult to not use technical terms. But okay, a state is
How did you keep your interest in physics of everything? Physics में मेरे सबसे कम number थे, by the way. I had 76, so I was ashamed of 76 in physics, and for me that was barely passing. So how did you get into physics?
So actually multiple reasons. To begin, मेरे नंबर फिजिक्स में सही थे. तो मुझे पता था कि there's something sort of something's clicking there. I have a certain flair towards fundamental sciences to begin with as I was growing up. But honestly, like, I vividly remember these sort of instances like when I was in high school. So I was, again, absolutely I grew up in a very so my dad's a music composer, my mom's a fashion designer. Physics kahan se aa gaya bhai? So like, I grew up in a musical household, and filled with arts and design and so on.
Your dad is Sarang Tyagi, right?
No, his full name is Rajiv Sarang Tyagi, but we share the same middle name.
Okay, got it.
Yeah. So while growing up, I mean, he is also like this movie buff. We started watching Back to the Future, and so he noticed that I had certain interest in the movie, and I had questions about time travel or ye sab cheezein. But again, academics was never, not even in the horizon. It wasn't a path that I really like. I wanted to pursue or anything. I was more into sports, actually. I was basically trying to become a professional cricketer. Yeah, I was like, doing sports all day long, school maybe like morning practice and so on. But the story goes that one fine morning after my cricket practice, I think it was cancelled or like cut short because of like fog. Delhi mein fog bahut zyada tha, so it was cut short. And I went to, like, I just came back to my classroom. It was grade 8 or something. And some other students, first benchers, the people, nerds in the class, if you want. I had no idea I'd become one, but anyway, there were some students in class that I hadn't interacted with a lot, but they were discussing this life cycle of stars. So stars are born out of gravitational collapse. First of all, 8वीं कक्षा में कौन डिस्कस कर रहा है ये, मतलब why were they कि क्या हो रहा है? तो like, I was just like, okay, I had nothing else to do. I just sat with them and I started listening to this weird conversation about how stars form and they eventually die, and also sometimes die forming what we call black holes, apparently the most interesting object in physics. So tab I had no idea, but I don't know, that conversation with them, mostly just listening, was not part of the conversation, just clicked some switch in my brain, and I was like completely shifted, like tangentially shifted my trajectory onto this physics path. फिर उसके बाद I started researching that what all of this is, started reading the obvious books, Brief History of Time, Stephen Hawking, and so on, and just like my interest just kept growing and growing, and physics throughout high school became my favorite subject. फिर coming back to the original question of exams, competitive exams, also there were like directions were engineering or like any medical professional, BSc or like physics honors, pursuing fundamental science was not something which was very common.
Yeah.
Also, like I said, my parents were not from an academic background, so I had little to no guidance in that direction. And then like I made a conscious choice कि नहीं भाई, मैं JEE exams या JEE mains और prelims or mains नहीं दूंगा. I will go down the BSc path, BSc, MSc, PhD. It was a struggle, or it actually, like, again, all your decisions are like double-edged swords in some sense. Because I had no idea that IITs back in the day, and even like state colleges like ICERs. So ICER is Indian Institute of Science, Education and Research.
In
And
Bangalore.
IITs. Bangalore, I don't know if Bangalore has an ICER. Bangalore has an IISC.
C, right.
That's
Right.
Indian Institute of Science.
Okay.
Also, Bangalore has like many other institutes. Raman Research Institute's there.
Yeah.
ICTS by Tata is there. Fantastic places to do physics.
Mm-hmm.
But apparently, those exams were also like an entryway for these other places, and I had no idea about that, and no one sort of like told me that this is one of the ways to do it. But anyway, like, I pursued a BSc in physics after my school. Again, consciously did not give these exams that would lead to, you know, that I constantly, I don't know, like, while understanding that I wanted to become a physicist and wanted to pursue fundamental science, I just did not want to be part of the rat race, which I could see. Coaching institutes, Narayana, FitG, blah, blah, blah. Everything's going on. People are like, you know, ye. Also, why the hell would anyone go to school अगर असली पढ़ाई, quote unquote असली पढ़ाई बाहर हो
Tuition
रही
होनी
है?
है.
हाँ, तो ये क्या हो रहा है? तो like, I made some conscious decisions. I was very much aware of this entire situation. Sat down with my dad and I was like, hey, I'm not going to give these exams. I don't want to be part of this rat race. I'll try to carve out my own journey. I think I'm fairly passionate about this particular subject that I want to pursue. And that's what I'll try to do. So that led me to this bachelor's in physics from Amity University. Then I also have a lot of things to say about that. We can get into it, but just to keep everything, like bounded. In Amity, I was fortunate enough to actually get a research, like a summer intern position at a fantastic institute in the middle of nowhere, again in Allahabad. It's called Harish Chandra Research Institute. My goodness, that changed my life post sort of realizing that I want to do physics. That told me how physics is done. Like, that was the place because it housed the best scientists and theoretical physicists in India at the time. All of them were there.
Is it this institute where these scientists from India were working in cohorts with people all over the world, and they're trying to like do the best work in all kinds of theoretical physics?
Exactly right. So back in the day, it had the best. There's a physics sort of community. It's called the quantum physics, the quantum information and computation physics community. Yeah. It had the best group in India. There's also another theory in physics called string theory. It had the best string theory group in India.
Wow.
Best mathematicians in India. One of the best, at least, people working there. You know, this famous guy Ashok Sen is a famous string theorist. He was there at the time.
Wow.
And I got to interact with him. I had a great mentor at HRI. So 3 months spent in Allahabad actually just like were absolutely fantastic, and they nudged me into the direction where basically I learned how theoretical physics is done, which is something, again, absolutely missing from like a standard education system all across India, I believe. Went for my master's after that to England, Durham University again. So basically, like, I found myself getting to the right places ever since I made the decision. I was fortunate, and I had the privilege, and I'm like I said, I'm very grateful to have been to these correct places, because, like you said, I mean, a small nudge in the other direction sort of takes away the curiosity from within, you know.
Yeah. I think like if what I'm getting from this is that usually it is that, you know, when our parents are either employed or in the sciences or in some sort of employed in the way like a corporate employment, not like business owners or whatever, they kind of have these ideas amongst their peers or whatever that, you know, my kid should go into a technology institute or something like that. Right. But the fact that both your parents are somewhere in the arts meant that they
Yes.
didn't create any impediments for you to pursue whatever the hell you wanted to do.
Basically.
It sounds like that, because otherwise the general idea would be that, oh yeah, you need to go to IIT. There is no
Yeah,
two
yeah.
ways about it. It's
Yeah.
either that or you're a failure. Usually that,
Basically, that's the
yeah,
norm. Yeah.
yeah. So that's great. And uh, another thing that I note is that, Amity University, Durham University, and even like Houston University now,
Mhm. Yes.
they are not the places one imagines a theoretical physicist to necessarily, uh, uh, I don't know, aspire for. Like, usually when I think about a physicist, I'll think of like, like in India, I'll think of like, I don't know, maybe like an IIT or whatever, and or maybe for sciences, I'll imagine like an Oxford or a Harvard or whatever. And what I see from you is that you're not bothered by it, and in fact, you've kind of like, although these are absolutely like amazing institutes, but they are not an Oxford or a
Of course, they're not.
IITK.
Yeah.
And
Yeah.
I think you're cognizant of that fact, and also you're unfazed by it. Is that fair?
Absolutely. That's true. That's right. You're absolutely right. So, scholarly sciences historically have been very, for the lack of better words, scholarly sciences have been elitist throughout historically. All great scientists that have existed, barring a few exceptions, of course, there are always exceptions, have come from academic backgrounds. So nepotism है वहाँ पे भर भर के है.
Okay.
ठीक है. In fact, there was a recent study by, so there's a Nature called Journal. Oh, what am I saying? There's a journal called Nature. There's a journal called Nature. It's a very prominent journal. It's a journal from England. It publishes work in all of sciences. It has its fans and haters and blah blah blah. Everything's there, but it's a very prestigious, very prominent journal, and people take it very seriously. They recently, like I think it was last year's Nobel, around the time when the Nobel Prizes were announced, which was given to everything AI, and there was like Jeffrey Hinton and so on, and Demis Hassabis from Google got the prize, and there was a divide in the community that, hey, what the hell's going on? AI ko kyun de rahe ho sare prizes? And anyway, the article said something absolutely mind blowing, which was that all the Nobel Prizes come from this extremely niche network of people.
Right.
And it has to come from, you have to be the academic grandson of someone to get a Nobel Prize. Us lineage mein, everyone has a Nobel Prize and so on.
Okay.
So like the joke goes as the following: the first चीज अगर Nobel Prize चाहिए तो जाकर Cambridge में पढ़ना पड़ेगा, UK में, और वहाँ पे भी एक particular some particular college, work under someone and so on. You can navigate, you can basically chart your Nobel Prize journey and so on.
Right.
And I was, again, like you said, cognizant of these things, and aware that, hey, I'm not from an academic background, so I have to sort of carve out my own journey in this world. In this world, there is, like I said, has a lot of nepotism, like any other place, and very elitist. You have to be absolutely financially stable, and to be able to pursue fundamental science, because fundamental sciences are anyways like 300 to 400 years. Theoretical physics, though, it stays 300 to 400 years ahead of the current time and technology. So in order to find my own unique path, not be bothered about the timeline, because you'll see stories of people coming from academic backgrounds, of maybe getting a PhD in the age of 22, 23, and from places like Harvard, MIT, Oxford, and whatnot, and they become professors at a very young age, and like I'm 28, 29 right now. I'm in my final year of my PhD. So like I said, I was on my own timeline, on my own journey. So I had to be completely aware of the fact that, hey, science has now been democratized. I know that the resources are out there. I have the right amount of passion for it to be able to navigate. So all I need is, an advisor, an institution where I can sort of do my work, think, and can provide me with the basic resources, and I'll be able to excel in what I want to do. So like you said, I'm completely unfazed by that. Sometimes it hits, obviously. I'm not gonna lie. It's not like usse farak nahi padta. Your institute carries a lot of weightage. If one is from some IIT or whatever, it'll carry a lot of weightage throughout your journey. If you're from an academic background, it'll help you a lot. The struggle reduces. So it bothers me at times, but then I always come back and ask myself that, hey, why did I choose to even... So again, a small anecdote from my time in HRI, that, I met this guy, Ashok Sen, and I was chatting with him, and he was like, and I asked him, why are you doing this? Like, what pleasure do you get out of this? So he said that the first thing when you step into fundamental science is that ये भूल जाओ कि पैसे तो नहीं है. There's no money whatsoever because you're doing fundamental science, and you're only doing it for yourself if you're doing like theoretical sciences and so on. Of course, I'm an advocate for fundamental science, and I've been doing advocacy as well, because I know like the breakthroughs that fundamental sciences can provide is just completely unimaginable. So sometimes you cannot foresee. For example, Einstein could not see that one day GPS में Einstein's equations use हो रही होंगी, and we'll be able to navigate everywhere on the planet. No one will ever be lost again. So he had no idea that this can happen. So all of the breakthroughs are sort of hidden in corners of fundamental science. So that's why it's required to do it. But this guy told me that, hey, you're doing it for yourself. B, there's no money. And C, since you're not from an academic background, you will have to find your own path, and you have to struggle, and you'll struggle to find mentors and guides to be able to, because everyone is sort of like trying to, and it's a very fiercely competitive scholarly field.
Yeah.
And so on. But yeah, so if I was bothered a lot by, is college mein nahi hua or us college mein nahi hua, then I wouldn't do justice to the science that I really want to do, physics that I really want to study. Also, to add to that briefly, science, like I said, has spread out and decentralized, if that's the correct word, from these central institutions. It has gone to other places. So now what has happened, honestly, is that you will find a lot of great scientists, physicists, whatever, at these small institutes as well. So at the end of the day, when you go for a PhD, what you have to look for is an advisor who's an expert in whatever field you're interested in. And that's one, because an advisor can make or break your career. That is it. There's no ifs and buts around that. If an advisor will absolutely make or break your career. And B, you should be interested in the problem that you're working on. These are the two primary things that matter at the end of the day, because science has sort of democratized a lot, and it has spread out to these even like the smallest institutes and so on that exists in these small corners. Like I'm collaborating with someone from Slovenia right now.
Okay.
From in Ljubljana, Slovenia, wow. the capital. It's like a tiniest possible country on the map and the tiniest possible city on the map. And this guy is the world leader in quantum chaos. That's what it's called. Quantum chaos is the community.
Yeah.
And he's literally the world leader. Like everyone wants to work with him. And I fortunately bumped into him in one of the conferences. Wow. And just started working with him, and he was, gracious enough to agree to work with me.
Wow.
But anyway, the point is, he never attended a single college or education outside of Slovenia.
Wow.
Born in Slovenia, studied in Slovenia, working in Slovenia, and is the world leader right now. So there are stories like these, and literally every physicist knows him. Every expert physicist will know who this guy is. Mm-hmm. So things like that happen all the time. But you just have to be sort of like, you have to, like you said, you have to be unfazed about, all these factors, and you have to just keep going.
Isn't Prachi better than you at quantum chaos?
Better?
Yeah? I think it was
interesting.
It was her research topic, right?
No, that's, in the whole like the complete technical detail, my research area is, it's called quantum many body theory and quantum chaos. So that's my area.
Oh, okay.
Prachi works in something called the holographic correspondence, or the ADS-CFT correspondence, and is studying this correspondence. Again, I can go over these words, but she's studying something called quantum chromodynamics using holographic principles. It's the theory of strong forces of nature. That's what her area of expertise is.
Okay, we'll get into holography, right?
Yeah.
What is that? Could you just maybe like a little bit on what is holography?
Okay, so holography it comes from the holographic principle, and literally from the fact that you know what a hologram is, which is that let's say you have a sheet of paper that has some information encoded on it, and you must have seen this, that you shine some light on it on this two-dimensional paper, or like whatever thin X-ray sheet or whatever, and then you get like a real life figure on your table or whatever.
Like
hologram,
a three-dimensional,
like a three-dimensional figure from. So the holographic principle, very loosely stated and sort of simplified, says the following: that all information about a three-dimensional object can be stored on a two-dimensional plane. So, if generalizing this principle, what happens is that if you're in sort of n dimensions, let's not give the dimension a number. So everything about an n-dimensional object can be stored in an n-1 dimensional object. So on a two-dimensional paper, you can store every possible information about a three-dimensional object, let's say, a figurine or whatever. So that's loosely what the holographic principle is. It sort of departures from natural intuition, because like when one thinks about like, you know, and like some information about an object, let's say a three-dimensional object. So the volumetric information is very important. And information, like if you want to describe a three-dimensional object, you need information in the volume of the whole thing. So you need three-dimensional information, very loosely stated. But the fact that a higher dimensional object can be completely described by information on some lower dimensional surface, let's call it that, is completely departure from intuition, because you need one less dimension to completely describe something else. So that's what the holographic principle is.
So the information is stored on the surface.
Yes.
And
that's right.
And therefore the area in a three-dimensional space is maybe more important for a quantum physicist than, say, the volume of it.
That's right. That's so I was refraining from using the word area, but I can.
Yeah.
So the information about the volume of an object can be stored on the area of the surface that it's bounded in.
Right.
Yeah.
Like this room, the information, all the topographic information or anything that I need is on the surface of it. The volume is kind of not that relevant in this case.
So, not exactly. So, the surface can have all the topographic. Right now, it's in the volume, but when you want to describe something in sort of this reductionist fashion, the surface is enough. The surface has enough area to encode all possible information inside the room.
Right. I'll pretend like I understand this fully. But which actually brings me to the question, which was my first question, which is that can a person of like a below average IQ like mine be in this industry? Because ek to ye ho gaya that you spoke about nepotism and elitism in a certain way. There's also that thing of this highbrow thing that, you know, oh, we are geniuses and there's a small community of geniuses. Like from outside in is what I'm saying. Is that it sounds like a very inaccessible thing for someone like me from the arts especially, that okay, I guess I'll go back and do some painting or theater, maybe this is not for me. Is that kind of is it possible for someone to get into it with an average IQ and then do really good at it?
Okay, so cognitive prowess and flair, some people call it that, is obviously required because even within the physics community, not everyone is Einstein.
Yeah.
Not everyone is, I'll name some other names, in modern times, not everyone is Juan Maldacena or Edward Witten. Now, why I took these names, because see, these are heroes of physics right now, among many other. I just took two names. There's so many others who are not part of, well, they're quite popular right now. So like people like, you must have heard of Brian Greene, Neil deGrasse Tyson, it talks
Brian
about
Cox, yeah.
Brian Cox, correct. So these are the three names I took later are what the physics community calls science communicators.
Yeah.
पर साइंस तो क्लासरूम में भी कम्युनिकेट हो रही है. मतलब it's not like if some people like myself enter the public domain and start talking about physics, they're called science communicators. और जो क्लासरूम में कर रहे हैं या कॉलेज रूम्स में कर रहे हैं whatever are still physicists. Anyway, why I bring this up is that there are people like Witten, Maldacena. So these are sort of heroes of physics, and they naturally come with like a higher cognitive ability than the rest, and that's why they're heroes amongst physicists, because they not only collaborate with other physicists and are pushing physics in various directions. They are like by themselves like great physicists who publish solo author papers with breakthrough ideas and so on. Coming back to the question, can someone with an average IQ excel in physics? Yes, because the physics community now has not just decentralized, jo we talked about earlier in terms of other colleges and blah blah blah, but also it has formed a lot of domains. So and it's sort of stagnated a bit right now. The physics. Okay, let me be very clear. There are breakthroughs happening honestly every day. People are doing fantastic research, but all the low-hanging fruits have been plucked.
Right.
Okay? So we're still waiting for new fruits to grow. And for that, you have to nurture the tree, take care of it, and so on, or the plant or whatever, and wait for these fruits to sort of grow, and then we want to pluck them again. But we're sort of in this growing stage where we don't see fruits right now. So we need creative ideas from other areas. Computer science, mathematics, chemistry, biology, and so on. Even the arts. We need courageous people to actually get into this domain. And because now it has so physics is much more collaborative now. Back in the day, the image was a lone genius in a corner.
Yeah.
Ek lamp chal raha hai, or the person is thinking. Physics is much more collaborative now. And rightly so. I mean, it's a team sport now. People have to come together with different ideas and work together. But honestly, again, the will to put in the work. See, if you do not have the flair, you will have to compensate it with a degree of hard work, which these other guys that I named, of two reasons. A, because they were geniuses in the physics world, and there were low hanging fruits. They completely wiped the whole forest. They completely wiped off all the trees, and all the fruits were gone by themselves. And they were also geniuses to be able to actually identify that this is a fruit and it's not poisonous, and we can actually eat it. So they were genius, no doubt, and there were low hanging fruits, so they could do it. But it's much more collaborative. So the answer to the question that can anyone make a career in physics, I would say yes, but you have to compensate not having a flair with a lot of hard work. But you still need to have the level of passion and patience to be able to do fundamental science. There's no alternative for that.
When you were talking about this time of sowing rather than reaping, I was thinking about how, and this I've written down as well, that how do you, because see, the way I understand it in my very layman understanding of these things is that theoretical physics implies that there is a certain lack of evidence, or like, not
Right.
evidence through maybe your there's logical reasoning. Of course, there's a reasoning and there's as much experimentation as possible, but of course it's theory.
Right.
And like you said, it's maybe 300-400 years into the future that you're working with things that are going to happen, or you're trying to understand what happened. um Let me see where I was going with this. So you can spend an entire lifetime on one research topic and
Absolutely.
maybe reach a dead end, or
Mhm.
I mean, theoretically. Or uh, you could work towards somewhere and think that this is a dead end, but actually there is something. If you only had pushed yourself a little further. Like, I was listening to this guy, Robert Greene, right? You mentioned Brian Greene.
Brian
Brian
Green.
Greene. Brian Greene.
Brian Green.
So he was talking about how he was wishing that his advisor or his mentor would have stuck with his research a little longer, and I think he abandoned and moved on to other things.
I see.
And he wished that he could have continued in that journey. I think they were talking about black holes, or I wouldn't know, but something to that effect.
Right.
How do you know that, okay, this is a dead end, let's maneuver somewhere else? Or how do you know that, oh yeah, okay, I know my mind is numb right now, but there's something mind blowing a little further ahead, so let me keep pushing.
Okay. So honestly, there's no way to know
Hmm.
something like this, because okay, so I think the first part was theoretical physics, obviously. Okay, the reason it's theoretical is because we're informing contemporary experiments that, hey, this is what we predict.
Right.
Try to look into this and see if you find something. So what theoretical physics does is, okay, one thing is that we can be absolutely unreasonable with our demands. भाई ऐसा experiment होना चाहिए तभी जाकर कुछ मिलेगा. But that's not fair, right? Because technology is sort of trying to keep up with what physicists and engineers are like, who work with like these fundamental concepts. Technology is always trying to keep up with us.
Yeah.
Let's call it that. Experimental technology. I'm not talking about like the regular technology, you know. But anyway, experimental technology, which later becomes like accessible
Commercial,
technology.
Yeah.
Experiment technology is trying to keep up, but as theoretical physicists, we have this responsibility to come up with smarter and smarter ways to actually do whatever's required with the current experimental setups that's available. Okay, so there's also a notion of indirect evidences. So you dig deep into, let's say, a theory, and you find that, hey, with brute force, I would need exactly these many resources.
Repetitions, yeah.
Right, exactly these many resources to be able to do something, to be able to verify what my theory is predicting. But let me work a little bit more and see if I can actually, with the current resources that I have, can I find some indirect evidence that would point towards whatever my theory is predicting. So that's a burden that theoretical physicists carry, and rightly so. Again, I mean, we cannot have unreasonable demands, because then what's the point? It's a collaborative science. So that's what theoretical physics, like, has to. Theoretical physicists, sometimes they don't care about it, but about hitting dead ends, let's come back to that. So as you also mentioned, Brian Greene, it is true that there's no way to actually find if there's like a breakthrough around the corner. Or so sometimes people work on things like work on problems for like years. So for example, Einstein came up with the theory of special relativity in 1905. And he generalized that theory to general relativity in 1915. That's a decade apart.
Right.
So he had to stick to this problem for 10 years. And let me also mention that he was competing with then mathematicians of his time who were much more capable and were approaching this problem from various other directions and had better resources. But what Einstein had was something very special. He had a nag for like he had a he had an immaculate or like he had immaculate intuition. Let's just call it that. He could see the end point of a problem first and then sort of reverse engineer everything. He knew where things are going to go. Of course, there are shots in the dark. It's not like you absolutely are aware of the answer. Sometimes people are, though. There are examples of that as well. But he could reverse engineer the whole thing, and so he learned resources along the way too. So had he not stuck to the problem for a decade, he wouldn't have come up with general relativity and, By the way, that's his. He was Einstein in 1905. He could have stopped. He came up with 4 intense papers: Brownian motion, photoelectric effect, special relativity, and another one. And so he got a Nobel Prize because of what he did in 1905. He could have just stopped. He could have just taken it easy, but he stuck to this problem. He wanted to understand the nature of gravity and wanted to understand all of that, and stuck to a problem for a decade to be able to reap the benefits or the fruits or whatever you want to call it. But that's not always the case, right? Because you need to have a good sense of where the problem is going. And being a scientist, you need to absolutely have an open mind about dead ends. There are times when your work hits a dead end and you should be able to let it go. Even accepting the fact that you're sort of like at the moment out of ideas, maybe some other idea can come up. And hey, that's why it's called research and not search. You're always trying, there's a prefix there. So you're always trying to go back and trying to understand what people had done, and you're trying to come up with input your own ideas into it and come up with better theories and that maps nature more closely and so on. So there are ways to identify. I can go over many technical details of what the ways are, but let me keep this general. The first way and something that you will obviously understand is money. Sometimes finances and the economy and the need for a country decides whether a problem is supposed to be pursued or not. So right now there's a lot of money in quantum computation, information, and AI, and how AI sort of integrates with physics. And that's where all the money is. And that's what sort of dictates, where your research should sort of also go, if not the only direction it should go in. Because, there's like a natural sort of, there's money being pumped into these pipelines where through which you're trying to understand how AI sort of integrates into this whole business and how AI can inform physics and so on. Simultaneously, you're also supposed to work on problems that interest you the most. So you need to find this balance of what interests you the most and what the current demand is, and also try to marry them if possible. If not, then you can keep them separate. But like I said, you have to be open about dead ends, and you have to stick to a problem for a reasonable time. Definitely in theoretical physics, for a reasonable time, you have to keep thinking about the problem. You're not supposed to sort of let it go in the first instant you fail. You have to keep working, and in the end also be very open about, so during the time when you're working on a problem, there's also a possibility that someone publishes a paper that completely destroys your foundation, all the foundations of your problem. And as a scientist, it's your responsibility to be absolutely open about that. So go and read that article and see what they've done and why what they did completely shatters what your area is or what your ideas were. And you have to be very, very open about that. And along the same time, also have problems and interpretations and approaches that you're absolutely passionate about. And you have to keep pursuing them for a reasonable amount of time. And like I said, in theoretical physics, that time frame is sometimes decades. Also, it depends on what the person is. You can be a hog or a fox. That mentality. So you can sort of keep jumping on different problems. People do that. I am closer to that. I try to move on to different problems and
a diversification of your portfolio.
Yes. But there are physicists, and those are also absolute. So, like I said, both these ends of the spectrum are required. That there should be physicists and scientists who sort of zoom out and see the bigger picture and sort of try to marry different problems. That has its own benefit. But but the other side is equally important, where you have to completely take a deep dive into a problem and just
all
keep
eggs in the
unpacking
same basket. Yeah.
Right.
So going a little back, you mentioned Einstein. You said that he had this ability of maybe having a hazy picture or some sort of an idea of what the end is going to be, and trying to reverse engineer what the path could be. So I'm just asking, obviously I'm not suggesting or implying that this is what Einstein did. I'm just taking it as a fictional example. That could it be as simple as writing down E is equal to mc square on the board and then thinking, is this true? Let me see. Is it like that, or is it like chronologically you reach that point, or do you propose that point and then come back to it?
Right. So I think what you proposed is fine. People do that. Sometimes they have an equation where they stare at it. It was not the case of Einstein. I mean, this equation was an outcome of a series of events that got him to equals mc square. Just like an object that has some rest mass has an energy equal to mc square.
Yeah.
But like I said, that was an outcome of this series of ideas that he had. It wasn't like, but that happens. People so let's say I have this equation, but let me write that down on the board and see what the two sides of the equality sign even mean. What's going on. So Einstein did a similar thing, qualitatively similar thing when he came up with general relativity. There was an equality sign, and on the left hand side of the equality sign there was something related to the energy and matter in the universe. And on the right hand side of the equality sign, very similar to E equals mc square, had something about the geometry. So that sort of people are like, wait, what? Like there's something about matter and energy that is equal to that is somehow dictated by what the geometry is. What's going on? So then people sort of he came up with this, of course, and he generalized the whole thing. And then people write down, it's called Einstein's equation. They write down on the board, and then they obviously stare at it, and it is very much true that we understand what Einstein did much better than he did when he did it. And rightly so, right? Because thousands and thousands of people are working on this, and they're using Einstein's equations on a daily basis if their research demands. And we understand that much more. But what happens is that when you write something like that on the board, you can sort of stare at it for a while and see where that equation sort of fits into whatever you're trying to do. And why is that equation important? There's, of course, a lot of details that I've swept under the rug. But then, that's true. That happens. People stare at equations and try to unpack and see because an equality sign is a very strong sign, by the way, in mathematics. If you're actually writing an equality sign between two things, it has to really be equal. I mean, you can't just two things are not just equal to each other, यूं ही. You know what I'm saying? So it has a very strong mathematical definition. It has come out of a lot of mathematical logic. And once you write that, you absolutely need to understand why what the equality sign says and why this is important, and need to have a picture. Okay. In fact, most physics articles and mathematics articles that you will read today, or you will come across, or anyone will come across, is the highlight of at least a theoretical paper is one of the two things. One, a plot, so a trend that you see, like a graph, or an equation which will have an equality sign. These are the only two things that, sort of ties the whole paper together. All of this, everything before and after is just like, building up to the point and like, concluding. But that equation or that plot is sort of the highlight of the whole thing. And that's what summarizes their whole idea. So like I said, an equality sign carries a very strong weightage.
Yeah.
It's very significant. You can't just like equate two things to each other.
And a plot is signifying some correlation between two things?
Right, exactly. You can have two variables that are somehow correlated, and the plot will tell you how exactly they're correlated. Is there a behavior? Is there a trend? Is there a law it follows after some time or whatever? And you can have more than one variable. So you can have a 3-dimensional plot or a 2-dimensional or a 1-dimensional or whatever. But you're right. I mean, it tells you how things are changing with respect to some variables. Okay. And now coming back to this whole intuition business. So this is one thing that you need to absolutely understand what an equation says, which is sort of the picture that you painted. The other intuition is about what the problem is and what's the meat of the problem. What are you getting at? So in the physics community, what people do is what we call, and it's like it's an approximation, and we call it the spherical cow approximation. Okay. So have you heard of this?
No.
Okay, so this is every physicist or mathematician sort of knows what exactly this is, but the idea is the following: you go to a physicist and you tell them that, hey, I want to solve this problem.
Yeah.
I have a cow. Okay, I have a cow. I want to calculate how much milk it produces, let's say in 21 days or whatever. So the physicist or the mathematician, the first thing that they will say is that let's assume that the cow is spherical, which is absolutely not true. So it's called the spherical cow approximation. Okay. It's become a joke, but the idea is that physicists have this, I won't call it habit, because habit sort of just like means that, they're just habitual of doing things, but it's the way to get to the meat of the problem. Okay, it's the way you get to what exactly the problem demands and what exactly you have to solve and build back up. So for example, like in your early middle school days, you must have, like, when we're introduced with Newton's laws and so on, F equals ma and all the 3 laws, and the law of gravity and so on. Every time we're doing an experiment or like some calculation, this projectile is going here and there, calculate how far it traveled or what's the height it reached and so on. We neglect something. What do you remember? What we neglect? We neglect air friction,
right,
or friction on the ground.
Right.
That's the spherical cow approximation.
Okay.
See, I will deal with all the friction business later. Let me see what exactly is happening. Let me give you an equation that will govern this.
So this is abstraction, right? This is
right.
This is
that's right. That's one way to
idea
understand.
Out of the reality of it, understanding it in isolation in an ideal situation.
Right. Exactly. So you understand an idea in this ideal situation, but sometimes the word ideal has a very negative connotation to it. कि नहीं यार, reality में तो friction है. ऐसे कैसे तुमने उसको neglect कर दिया? That's not true. If we don't neglect friction, if we actually don't get to the meat of the problem, people don't understand that adding friction, well, in principle it's hard because it makes the computation much more cumbersome and complicated. But the mechanism underneath is, you will only be able to identify that mechanism when everything is sort of ideal.
Right.
You have to assume some ideal conditions to be able to identify what the fundamental mechanism is behind everything. Yeah. And then you can sort of build your way back up and add, more and more complications on top of it. So people sort of assume that, bhai, theoretical physics mein you always assume things are away from reality. That's not the case. You have to do it, otherwise you won't be able to get to the meat of the problem. So so this intuition business, again coming back to and sort of closing in the whole thing, this intuition business is you assume the cow to be spherical. You need to be able to have a very strong physical intuition grounded in reality because, well, you're trying to understand the world around you. And you need to have this intuition, very strong intuition. Well, not everyone does. So, and you learn to have better and better intuition along the way. And sometimes people actually don't have any intuition, and they also succeed because there are other ways of doing it, and we can get into that. But anyway, if you have a strong intuition that what the meat of the problem is, how you can get to the whole fundamentals of whatever you're solving, you need to be able to see that. And that's what the end goal is. When I say there's an end goal, you need to see where the mechanism, what's the origin of all of this. And once you're able to understand that, you can sort of, again, introduce more and more complications and, add more quote unquote reality to the whole problem. Make it more ontological. Sometimes people call it that.
Open? Like an open system?
Right. So open system, correct. So correct in a very qualitative sense. But so open systems are, well, not closed systems for a lack of a better definition. But open systems are where you allow this. Okay, so when you're doing quantum mechanics, when you're solving like a quantum physics problem, what you assume is that this that you have a system that you want to model using mathematics and equations, and that system has to be shut off and completely isolated from any environment that it is in. So within a universe you live in, you create a subset or a sub-universe where you place your system in, and you assume yourself to be outside of this subsystem, and you see how this subsystem evolves with time. Okay? That's what people do. Now, this statement that I just said is loaded with philosophical baggage. If there was a physicist in front of me, they would have stood up and started shouting that, what the hell is going on? And that's true. Because I'm trained by my advisor and the physicists that I idolize and I've met along my journey. And so I have my own philosophical baggage in all of this. But a lot of people have some different ideas. But anyway, let's not get into that right now. But the general way is to isolate a system and study the system over time. Yeah. See what happens in the system. Now, what you do is that you, onto that subset, you add another layer outside. So you allow it to interact with some sort of environment. Okay. That's when the system becomes open. Okay. When a system becomes open, still you're assuming that whatever the interaction with the environment is, it's not bothering you much. So you don't care about that interaction. But once you want to care about that interaction, that's when you're actually in this open system business, and you're trying to understand how these isolated systems also talk to their environments, and what changes do we get doing the same thing. We're only trying to understand how a system evolves from point A to B. Okay.
So what is the kind of noise or elements that we are introducing in the peripheral system that will interact with? Is it like gravity? What exactly are we trying to introduce?
So that's right. So it that depends on the type of problem that you want to solve. So you're right. I mean, let's say you're studying a system on our planet or any other a place in the universe. It's absolutely not possible to not accommodate for gravitational effects. Okay, because gravity is universal. It's a fundamental force, and it acts on everything. Okay, and it's a very mysterious force. Again, perhaps we'll talk about that much more. But we have theories and equations that neglect the effect of gravity, because we say that in physics terms, it's called that the effects due to gravity are subdominant. They're not dominant. Yeah. Okay. They're not dominant effects. So the physics jargon is that these effects are subdominant, and what that simply means is that whatever gravity is doing to the system is not relevant given the type of forces that are involved within the system. So if you have a ratio of whatever the forces that exist in the system to the force of gravity, if that ratio is 10 to the power of minus whatever 50, so then that's basically zero, right? Yeah. Right. Although it's not, but gravity is still there, right? I mean, you can't. So you neglect all subdominant effects, and you try to understand what your system is doing.
This is, by the way, a quantum system, right?
This is a quantum system, correct? Or even a classical system, honestly. I mean, when Newton came up with laws of motion, I mean, he was not like when we're thinking about objects, moving in straight lines and so on, he wasn't really bothered about gravity.
Right.
When we solve high school problems, we're not bothered about gravity unless we're asked to introduce gravity into the whole mix.
Right.
So as soon as in classical physics, gravity is not subdominant. You need to have gravitational effects to be accounted for when you're doing classical physics. When you're doing quantum physics, in scenarios that gravitational effects are subdominant, so you can actually neglect them. But again, they're not there. Right. So in the end, you want to introduce everything back if it's actually making a difference. If it's not, then even introducing gravity back into the picture will not change anything. But if it is, then very much you have to sort of place everything back. So in this case, gravity was sort of the environment, or something like, or that you introduced. But an environment is sort of this parent umbrella term that can be attributed to many things. So one thing, let's say you have a chamber of like a metal chamber, and in the center of this metal chamber, you place like a material or something. And you shine some light into this metal container from, let's say, like a small pinhole or whatever. You shine some light and then you close off the pinhole. So there's photons inside the metal container now that are bouncing around. So that's your environment then.
Right. Okay.
Your system is the material that you placed in the center of this metal container. And there's mirror inside, so light's just bouncing around and doing all sorts of things. So that's your environment. So environment in physics generally is something that you're not bothered about much. But in order to get the full picture, you want to introduce the environment and see how this is interacting with the environment. Also, again, there's plenty of philosophical directions that we can go into. What do you even mean by environment? Who decides a strict demarcation between what the system is, what the environment is? Because we're beings within a universe. We can only imagine being outside the universe, but that's not the case. We're inside of the universe, and being inside the universe, we're naturally interacting with all sorts of environment around us. That has a back reaction onto how we perceive the environment and so on. So again, just to tie everything together, environment is something that that physicists are not very much bothered about unless the system is open. As soon as you open the system, then you're seriously worried about how it interacts with the environment. What the environment is, it just depends on what the problem you're solving. So like you said, gravity could be something. A gravitational potential, as people call it, could be an environment of like a cavity. Photons could be, or even some thermal temperatures could be environments that you're not very much bothered about.
So this is where decoherence comes in?
Correct. Yes, that's right. So decoherence is the phenomena of which systems uncontrollably interact with their environment.
And this is a fairly new quantum term, right? Like in the 90s or early 2000s, decoherence was not even taught in quantum physics, as I understand.
Correct. I'm slightly missing out on who came up with it first. Was it John von Neumann? Anyway, don't quote me on that, but some great physicist did come up with decoherence. The idea of also it evolved as sort of, and there are alternatives to decoherence. Also, I'm not familiar with at the moment. But okay, so decoherence. Before I tell you what decoherence is, let me tell you what the problem is. Okay, the problem is, again, carrying a lot of philosophical baggage. The problem is, the world is inherently quantum. The world at the microscopic level is quantum. At the quantum level, the world is quantum. However you want to phrase the whole thing. And out of that quantum world, a classical world emerges.
Right.
So again, a lot of physics terms in this. First of all, what the hell is emergence? emergence is how something emerges out of something, so again, a fantastic thing about our world is that isolated objects have a completely different behavior than collective objects. Objects collectively, so particles collectively, behave very differently from isolated particles, so like one particle. And that collective behavior is called emergent behavior. Okay. So as we move out of the quantum world and into the classical world, which you and I see on our daily basis, has been quote unquote decohered. Okay. So decoherence is sort of responsible for bringing us out of this quantum world into the classical world. So first of all, this transition is an open problem in physics. So now the word open is being used in some other context.
Yeah. This is like where now no longer in a classical world, superposition is not possible, entanglement is not possible, teleportation is not possible.
Right. Yeah. All of these quantum effects that come from like a quantum world are not possible.
Yeah.
And you're in a classical, very clockworky sort of world, and you can predict. In a classical world, we can mostly predict everything.
General relativity applies.
General relativity completely applies at large length scales, and Newton's laws apply at these mesoscopic scales and so on. So we've sort of come out of the classical world. So it's an open problem in physics. People have no idea. They have many ideas, let's call it that, of how this happens. But there's no one idea that everyone agrees upon that how this has happened. There's also like a great idea. I have my disagreements with it, but it's a great idea nonetheless. It's called quantum Darwinism. That tells us how this happens. So that was one alternative to decoherence. It's called quantum Darwinism. You can read about it, and your listeners can read about it. I have my certain disagreements with the idea, but again, it's a fantastic idea because it's an idea in the first place. That it's impossible to actually come up with such ideas.
Could you summarize it in like one line?
Quantum Darwinism is basically it's a way how it's basically like Darwinian evolution. So there are certain quantum states that survive this transition of becoming classical, and these are called pointer states. So what is a state? A state is all of this is very difficult to not use technical terms. But okay, a state is a state is a state of being, let's say, in the sense that a state carries a lot of information. So let's say you have a list of numbers or a list of information that defines that my coffee cup is green in color, has black coffee, has a certain temperature, and can do this and do that. So again, very qualitative definition of what state
like a complete
is. So that's
description.
The complete description of what this coffee cup is called a state in physics. But in quantum physics, the state has much deeper meaning. But let's just call it that now. So when you transition from quantum to classical, there's a certain way of selection. So natural selection is where this is borrowed from Darwinian natural selection and how things evolve. And quantum Darwinism tells us that there are certain states that survive. These are called pointer states, and they're called pointer states. Pointer simply means that they're pointed in some direction that survives. And in order for all of this to transition into like a classical world, what happens is that they interact with fragments of environments that is enough to tell you. So for example, there are 20 photons bouncing off of your face and entering my eyes. And those 20 photons are enough to tell me that, hey, you're a person. And right now you're doing a podcast with me and so on. It gives you enough information to actually identify what this is, that you're a human being and so on. So that's what quantum Darwinism is. Quantum Darwinism just tells us what certain states survive this quantum classical transition.
So whatever we are seeing is actually what has survived.
Right. Survived certain conditions that again for the podcast are irrelevant right now. But there are certain conditions. There's certain conditions that these states have to sort of checklist
Yeah.
There's a checklist. As soon as you go through this checklist, you automatically get like an outcome of these certain pointer states, they're called, that survive, and that's what you see in a classical world, in an experiment. So by the way, any experiment we do in a lab is a classical experiment, because we're actually taking the quantum system out from the quantum realm into the class. So you, at the end of the day, you get a number.
Right.
It could be a click or a whatever, but
Right.
it's mostly clicks. So all physics experiments are clicks. Something happened, click. Something did not happen, nothing.
Okay.
Basically, that's all experiment. But then it's oversimplified, of course.
yeah.
But basically, that's what it is. All of them are clicks.
Yeah.
So it's all of them is counting. So you're taking a quantum experiment out from like this quantum world, this microscopic world, into this macroscopic world that we see around us. So this transition happens as you're doing this experiment. So automatically there's so many philosophies and so many approaches involved, that how do you even approach this? And so quantum Darwinism is one of them. Decoherence is another one. Decoherence is, again, a way of transitioning to the classical world, but decoherence is much more simpler. It says is this uncontrolled interaction with the environment that the quantum system sort of entangles with fragments of the environment. So there's still quantum effects surviving,
Okay.
but this entanglement is so widely distributed that you don't care about it anymore.
Okay.
And your environment uncontrollably interacts with your system. Let's say the environment right now, because I have lights switched on, there's like environment is filled with photons. So if I did a quantum experiment right in front of you, within fractions of second, more than the processing power of my brain, it'll interact with the environment, and I'll see like a classical version of whatever this experiment is. So I'll see a number or like whatever experiment I design.
Okay.
So that's what decoherence is. Decoherence is this uncontrolled interaction with the environment that leads to this classical formation of whatever object you're studying, and it's something you see in the classical world. So seeing, again, not necessarily seeing from naked eye, but like in an experiment, you get a number out of it or something like that.
And then, as I understand, you're trying to maybe control the decoherence or use it like a switch of some sort.
Right. Correct. So if you want to, so that's right. So the direction that we're sort of now maneuvering into, the idea is that when we're doing quantum experiments, so theoretically it's all fine. I mean, in order to not have an environment, I just have to erase a term. It's completely fine, from my equation. But experimentally, that's not possible. There's no way to erase the universe, So what happens is that in an experiment, your environment is automatically interacting with the system. So one, you have to minimize that effect. Okay, you should try. We want to try to minimize that effect, because quantum mechanics tells us that isolated quantum systems do this, and under certain approximations, open systems do that. Okay, so that's what we have right now. We have a very robust understanding of quantum mechanics as a tool, not as a theory of reality, because there, again, a lot of philosophies and metaphysics sort of comes into the picture. But as a tool, beautiful, complete grip of what the theory is as a tool. So we can use it as a wrench, like a very, very less opaque black box. So we can almost see through it, but just not quite. There's some blanks that we have to fill, but we more or less have a very solid understanding of what it is. Okay. So A tells us what isolated quantum systems, or like sometimes called closed quantum systems, do. And what open quantum systems do, also we have some idea. Under certain approximation, we have a great idea of what they do. So when we're trying to build like a quantum experiment, so let's say let's use the word. If you want to build a quantum computer, what we want to do is that there's an object in a quantum computer. It's called a qubit. Again, it's a state in Hilbert space. So it's in this abstract space. It's a state that I referred to earlier, because it carries some information. It tells us whatever we're studying, what it looks like in this mathematical language. It's called a qubit.
It's some sort of a pairing, right? As I understand. Yeah.
Right. It's a superposition.
Yeah, okay.
Essentially, it's a
Yeah.
superposition of two states. That's what quantum mechanics allows us. It allows for superposition.
Exactly.
Okay.
Yeah.
That's what a qubit is. It's a vector in a two-dimensional Hilbert space. There you go. That's the full-blown definition.
Yeah.
If anyone's curious, it's a vector in a two-dimensional Hilbert space. That's what a qubit is.
Mm-hmm.
Okay. Anyway, so there are many qubits because those are the objects that are gonna perform these logical operations that a computer does.
Right.
So there's 0 or 1 or a combination of 0 and 1.
Yes.
So those are the things that are going to do all the logical stuff to be able to do like any calculation. 1 + 1 = 2. I mean, even something as simple as that. These qubits need to be they're qubits on a paper, like I said, don't matter. But qubits in an experiment are real things.
Mm-hmm.
So they can be like, what's the best way to explain this? So quantum objects have something called spin. So they can be some opposite polarization of an object, 1 or 0.
Like a head or tail.
But these are real things. Like a head or tail. I mean, so head or tail is a good analogy on a coin to be able to understand what a qubit is. But in a real quantum experiment, there's much more subtlety involved. It's not exactly head or tail. But anyway, we can stick to heads or tails. Right. So in a quantum experiment, what happens? These qubits are the ones that are going to perform logical things, and these qubits are real. Okay, they're part of the world. Real as in they're real things that's happening. It's not equations. It's not numbers. It's not symbols, Greek symbols. They're real objects that when we study will perform these logical operations on a computer.
Like you give them a function and they'll perform something.
Whatever you input.
Right.
Okay. Correct. Right. So these real things also, since they're real things, they live in this real world, they will interact with the environment.
Right.
And quantum mechanics is absolutely bad when it comes to interactions with environment. Quantum objects want to stay hidden.
Mm-hmm.
They want to shield themselves from the world to be quantum mechanical. As soon as you shine some light on them, you try to see what they're doing. They interact with it. And interaction in quantum mechanics has a back action, or a back reaction, if you want to call it. The back action is that, since the environment is also fundamentally quantum mechanical, there's a quantum mechanical interaction between the two, and they both influence each other. So all the logical operations that a qubit is supposed to, or a set of qubits, like a collection of qubits is supposed to perform in a quantum computer, that gets destroyed because of this action with the environment. That's why you will see whenever you Google like a quantum computer, you will see, or like you search on the internet or whatever favorite LLM you have, you see you try to understand what a quantum computer is.
Extremely cold in a very...
Extremely cold, correct.
Yeah.
Very, very close, sub 50 Kelvin temperatures and 20 Kelvin or whatever, 100 Kelvin temperatures. You have to be absolutely very cold for things to sort of function well. So that way you're removing any thermal fluctuations in the environment. So there's no temperature fluctuations that sort of destroy and so naturally what happens in physics, when you cool something down, overall motion sort of slows down. So it's almost, think of it as like this slow-mo, that things are now, they're still interacting, but they're interacting slowly. So in the time scale of this interaction, your quantum system can do whatever the hell it was supposed to do, whatever the hell the function wanted it to do, and then it can interact with the environment. We don't care. So we just want to slow things down.
Okay.
That, let our quantum system do what it wants to do, and then it can interact with it. Otherwise, when it's fast, when the temperatures are high, everything's bouncing around, very jittery, very violent, and everything's interacting with everything, and whatever you want to do, the logical ideas get lost from a quantum computer. So that's the role of what the environment is and why you want to minimize this effect. Yeah. So an ongoing theme, again, just to sort of come back to the whole thing, an ongoing theme of my own research, something that I'm actively doing right now is the study of open quantum systems. And what we do is that we flip the narrative. We're like, hey, maybe, so again, bold ideas have like And honestly, it wasn't my idea. It was my advisor's idea, but I really found it very interesting, and I added my own flavor and sort of into that. So credit where it's due. So he tried to flip the narrative that what if we're actually thinking, we always thought that the environment is sort of this enemy, and it's sort of destroying the quantum state. Let's try to see what if it actually is an ally. And his intuition comes from the fact that, with the same philosophical baggage that, hey, world is inherently quantum, and plants have. So let's say you have a plant at the bottom of the ocean, bottom of the Pacific Ocean or whatever, the Mariana Trench, the deepest point, and there's sunlight only during the day. So a plant at the bottom of the ocean has to survive because photosynthesis requires light. Light is quantum mechanical in nature. So what's happening is that the photon travels from the sun to the surface of the ocean. Ab ocean pe hai, but it has to go all the way down.
Down, yeah.
So of course the sun is like an abundance of photons. So ek photon to nahi hai. There's like many photons. Plethora. There's enough photons, abundance of photons, and only one or two reach the plant. It only is getting this grain of food. So it has to make sure that despite all the noise, the ocean, plant itself, and any quantum mechanical noise, all the temperature fluctuations, it has to make sure that the photon gets to the correct site, to the correct receptor, to be able to carry out photosynthesis and so attach to the chlorophyll molecule and all of that. Okay, so that was his idea. He was like, see, if plants have been doing this for billions of years, millions of years, then there must be a mechanism to be able to understand what how this environment sort of aids energy transport. It's called quantum energy transport. How does it aid that? So I found that idea to be absolutely fascinating, and especially it was motivated by such a natural picture. And that's when we started thinking that, let's say we have an environment and, what if under certain circumstances, this environment actually becomes an ally to the quantum system and not a friend. So how is that advantageous? That's advantageous because then we do not need colder temperatures also require, money, because we need better refrigerators. Yeah. And refrigerators work on thermodynamics, so there's always heat transfer. There's refrigerators are pumping out hot air, and they're consuming a lot of energy and so on. So what's like a better way if we actually treat this noisy environment as some sort of ally? Maybe we can actually still study the same quantum system, but with much less resources that now get into. So it's a sub-problem. And then, it ties into this whole decoherence business as well and so on. It has many other implications. But when it comes to building better quantum computers, this is something that will definitely help.
Oh, okay. So this has a very real-world application.
Yes, very tangible, very real-world application to building this near-term quantum computers, if not
But this will still require some sort of a switch or a gate or some object or instrument to be able to harness this noise into a ally, right?
Right. So right now it's a theoretical idea. It's on papers that we have. But we have some ideas on how, so because we're motivated by this plant at the bottom of the ocean was this abstract motivating idea. But real systems motivate this idea because they have something called correlations in nearby sites. So think of a system, let's say the system is surrounded by some sort of environment, but environment that is adjacent. So neighboring environment is what it's called in physics. So the neighboring environment has some sort of correlated behavior. Similar to stocks, actually. So all of this is connected to, even finance. But anyways, it's called stochastic behavior, stochastically correlated behavior.
Okay.
These neighboring sites have. And because of these correlations, an environment very right adjacent to your quantum system sometimes creates domains that the environment basically, in simple words, shields itself.
Okay.
So just completely cancels itself out and it does not act on the system. So it's motivated by real examples, and we see that happening all the time in systems. But we need like a strong theoretical model. So I personally am working on like building this idea and formulating the whole idea into and thinking on different systems. There are other colleagues of mine working in the same group with the same advisor. They're doing more computational stuff. So again, coming back to the original question, if you have a more computer science flair or like a different flair altogether, how do you contribute to a problem? Because things have now integrated into this whole big physics picture.
Right. And I think if you can just jump domains a little bit, I have a small question, which is, as per your understanding, what is God?
Just straight went into it. Like, let's just. Okay.
Since this conversation was not heavy enough, let us.
Let me also go ahead and ask. So I think about all of this a lot. Again, I have a very sort of proliferated boundary of what God is right now, and I think मैं science की तरफ से हूँ. That's the.
By the way, interesting term, proliferated boundary. That means that you're kind of like agnostic. Is that?
I kind of am. Yes, I'm definitely I'm more towards atheism than I find great pleasure in actually trying to understand. In one of my recent podcast episodes that I did with Professor Ramakrishna Hosur, who's a Padma Shri awardee, is a great scientist from India.
Oh wow!
What really interests me is studying Vedic sciences that have propagated. So the means of propagation is stories of gods, and and coming up with all our epic texts, and so they're rooted in this story where there are godlike figures. But a side interest of mine, not so much side anymore, because I sometimes very actively think about it, is that Vedic sciences have a lot of potential if people sort of try to understand them from a scientific lens and not
religious sense.
And not a religious lens. Religious and the philosophical lens is there, how one is supposed to lead their lives, and on a day-to-day basis and so on.
Like lifestyle dictats. That's a separate topic. Yeah.
That is separate, but from a scientific lens. So like if you even start questioning like traditions revolving around eclipses and things like that. And why you're supposed to fast during like a change of seasons and so on. And so, like I said, if you put on your science hat and try to approach this, there's a lot of breakthroughs that I believe are inside of there. So, like I said, like coming from my family background and so on, I was surrounded by these stories as growing up. Stories of Mahabharata, stories of Ramayana, and so on. And I was very much interested. I did my fair share of reading and so on. But as I became a physicist and started learning this, I found this keen interest. Like I started becoming more and more interested on what's the scholarly aspect of Vedic sciences and I had a very deep conversation about this. Basically, this because. This Professor Ramakrishna Hosur has dedicated all of his retirement life to this, to understanding what Vedic sciences are trying to tell us, and is there like a scientific breakthrough hidden somewhere there? So that I was really interested by that. I mean, I only had them on the podcast because I was already interested in something like this. Anyway, how I think about God is. That I'm very open-minded in that sense. Again, that's also the scientist in me. What I align with the most is that, let's say, God in the form of a creator. There is no creator required because of the physics that I now know. So the requirement of any creator is obsolete. The universe knows how to take care of itself and originate, evolve, and end. And all of this is backed by theories of physics that are yet to have like concrete proof. There's problems there. For example, the Big Bang and so on. So there's like this inflationary period that we suspect and has a lot of problems with it, how it ended, how it began. All of this falls under the area. The domain is called cosmology. By the way, cosmology historically was basically a taboo science. People thought it was stupid
Astrology.
and so on. Astrology again, you can call it forgotten science or something. But definitely, massive objects cannot have any influence over our scale objects. So let me just say that it's not true. It's false. I mean, it's false narratives.
Of course, I mean, you're not a cosmologist, but so I'm not going to grill
I'm not a
you
cosmologist.
on this topic per se specifically. But generally, from your quantum understanding of the world and the kind of physics you said that you're aware of, you said that now I believe that creator is not necessary. Could you just like elucidate a little bit on that? Why you think so?
So the argument, the statement I said is mostly motivated from the it's called quantum cosmology. Actually, it's this merger of the two areas of physics. So when the universe originated, it was a quantum object.
Okay.
And then it transitioned into a classical object.
What you said was emergence of this classical
the
world.
Universe, right? Exactly. So the universe emerged as the universe itself, as we understand it now, excuse me, is what seems classical at large distance scales, was once quantum.
Okay.
So it emerged from a quantum sense. We understand how that sort of happened. It's encapsulated. Right now, the current model is called Lambda-CDM. Okay. Lambda is the cosmological constant. CDM is cold dark matter. Okay. So it's called the Lambda-CDM of the beginning of Lambda-CDM model of cosmology. Okay. Lambda tells us the following. Lambda, which is the cosmological constant, tells us if you remove everything from space, like if you remove all the matter content and if it's just empty space, it still has some energy. Okay. It's called the ground state energy in physics. Okay. So every object has, every object. That's true. Every object. The statement. Every object has some ground state energy. Okay. So you can now question, "Wo kahan se aayi bhai?" So where did that ground state energy come from? And then there are models that tell us that that things can emerge out of nothingness, because we know that so right now the model is called, again, the quantum aspect in all of this comes from something called quantum field theory, which tells us that the fundamental objects in the world are fields. Okay, they're fields propagating in space-time, irrespective of any reason. Nothing obstructs them and so on. And any disturbance in the field is what gives rise to a particle. And these fields are sort of what the fundamental thing is in the universe. It's called quantum field theory.
Yeah.
So the universe emerged out of these quantum fields. So there's always ways to emerge out of quote unquote nothing. So I know that things can emerge out of nothing. B, there's a ground state energy in the universe. So that ground state energy is sort of this driving, and it's abundant ground state energy because there is no non-ground state. So there's ground state energy that's fixed. So there's the infinite source of energy in some sense. Again, I'll be offending a lot of physicists when I'm oversimplifying a lot of things.
Yeah, but please do.
But anyway, the idea is that there's this ground state energy, which is this abundant source of energy, not for classical systems, but for quantum systems. It's not like you and I can access that ground state energy and build some battery out of it or something, and that is perpetually going on.
Got it.
So this ground state energy is quantum. It's in the sense it's a fixed number. It's quantized, that ground state energy. So it can only have certain values. So even the first excited state has a certain value. So it's like so for example, you can go from let's say energy units 1 to energy unit 2. You can't have energy units 1.5 because that's what quantization means.
Okay.
Yeah.
Okay.
So it's quantized. It has certain quantized fixed energy levels.
Okay.
But the ground state has some fixed energy that sort of drives the whole universe. It's responsible, again, conjectured that it's responsible for the expansion of the universe that we currently see. And there's in the Lambda-CDM model, so that was the lambda, the ground state energy. CDM is cold dark matter, which is, the dark matter that is not accounted for. So the first thing is dark energy. Lambda is called dark energy. And the CDM, cold dark matter, is dark matter. So it's a model that accounts for both dark energy and dark matter and has everything else that we know of physics right now. It's called the Lambda-CDM model of cosmology. And it tells us how the universe sort of evolved, went into, how it evolves through various phases. So by the way, the universe had a lot of, in the physics jargon, it's called phase transition. So phase transition literally is like changing of a phase. So a universe went
like water freezing.
Like water freezing. Freezing is a phase transition. Correct. Yeah. That's right. So the universe went through many phases. There were initially all the fundamental forces: gravity, electromagnetism, strong nuclear force, weak nuclear force. They were sort of combined and they sort of decoupled at certain epochs. They sort of moved away, and so believe it or not, at some point in the universe, and the photon did not decouple. So decouple simply means stopped interacting.
Okay.
Before the photon had decoupled, the universe was like, was red and like bright and so on, because it interacted with the matter that was there and so on. It still interacts with matter, but it wasn't decoupled. But then the photon decoupled at a certain epoch.
Okay.
That we know exactly, and there's a mechanism for it, and we understand it fairly well, not like very well. And then the universe became dark.
Right.
Otherwise, it was like this.
So light was all over,
scattered. Right.
Got it.
And then the universe, when the photon decoupled, stopped interacting with certain things, it became dark. Anyway, so the universe went through many phase transitions, and went through many phase transitions, and we understand that. So that's point C. So ground state energy having fundamental fields, so can come from nothing. We understand how it evolved. We understand astrophysics tells us how galaxies form, how planets form. Earth and planetary sciences tell us how planets evolve. So you see what I'm getting at, right? There's no need. Agar hum samajh pa rahe hain, so there's no need for someone to
design this.
Because we understand. Now, the subtlety is that, which maybe just warrants like a completely separate podcast episode, and I'm happy to do it, but it's called the fine-tuning problem. Okay. So our universe is fine-tuned. So there are a lot of philosophers also come in that, why do particles have certain mass? There's also called the hierarchy of mass problems. You start with certain mass and you build towers and towers of masses. How do you understand this? What's the distribution like? Why the neutron and the proton have the same charge but slightly different mass? Why the value of the cosmological constant is very, very small. So some parameters are fine-tuned. It's also called the naturalness problem. There's many words for the same thing. But our universe, no doubt, for lack of better words, is fine-tuned. Who the hell fine-tuned our universe? Like, it's basically all the knobs are tuned in the right direction. There's many arguments. Again, it warrants like a completely different episode. But there are arguments for a creator to exist there as well. So I'm giving you like
Food
both
for
sides
thought.
of the
Yeah,
coin.
yeah, yeah, yeah.
Yeah.
But there is, I mean, I've heard you specifically use this word a lot, which is, elegance. Like,
Right. Yeah.
so is elegance also part of this somewhere, or is that something else?
Right. So I have a tattoo
Oh,
that says
wow.
elegance.
Oh, wow. Lalitita.
Yeah.
Ha, ha, ha.
Yeah, it's Lalityam.
Yeah.
And I got it because, elegance means a lot to me. Because
Uh-huh.
any physics theory, I believe, again, it's a matter of taste and sort of preference. As a physicist, how you grow up, who do you idolize, and so on. All of that, all the baggage you carry. And the idea is that any theory of physics needs to be very elegant, very reductionist, and this also is derived from our Vedas, that certain shloks are written in like their couplets almost, but the meaning is you
Explosive,
can
yeah.
spend decades and decades to understand what So I always quote this, that the first line of the Brahma Sutra is Athato Brahma Jigyasa, which simply means let us now be curious about the universe. So this is the beginning of a book. And the first thing is that let us now be curious about the universe. So there's like the first sense, before actually even digging into the book, the author is trying to tell you that, hey, turn on your curiosity. Like now is the time to ask for questions.
Thinking hat, yeah.
Yeah, the thinking hat. You put on the thinking hat, correct? Absolutely right. You put your thinking hat on, and then you start thinking about, what the hell is going on around me, and why am I supposed to think about all of this? What does it even mean? So anyway, elegance plays a very sort of subtle role here. Is the fact that once you understand the bigger meaning, you need to package it into this elegant form, and that's how it's gonna propagate. And physicists chase elegance left, right, and center. They don't agree to it, but everyone does. They want to come up with E equals MC squared.
Yeah.
Okay? So you have to. They're always chasing it. Sometimes they deny, but they're always chasing this reductionist sort of argument, which is, hey, let me say 3 words and exactly. Let me try to package everything into this very small, elegant equation. Clean, nothing too crazy. And that's why E equals MC squared propagated. Like, people don't even know what it
The
means.
meaning, right.
Right. And it propagates that way. So that's where sort of, in my opinion, elegance comes in. And, this every physics theory, here's the statement. Every physics theory, in my opinion, has to have some sort of elegance. Behind the curtains, it can have all its, complications and problems and so on. It's like even with roads, we do this. We make buildings and so on, or uske piche there's,
scaffolding, which is like very pretty, yeah.
Exactly. The scaffolding, which is that's very, very, very well put. Yeah, correct.
I think you can hide a lot of like those loose ends behind those Greek symbols, and this is what it is, Well, very interesting.
Correct.
Okay. Okay, I think I'll not take more of your time. Maybe we can do a part 2 sometime if you're up for it.
Definitely.
Because this
more
is,
than happy.
I think we have just barely scratched the surface right now. But just a last question, maybe. Then I'll let you go.
Of course.
Let me see which one I want to ask. Although we have not gone through the list that I prepared, but still I've gotten a lot of answers. Let me just ask you the final question, which is, which I ask a lot of my guests actually.
Okay.
So I have a magic wand, and you spin this magic wand, and no ethical issues, no limitations of resources, no problems. You just have a magic wand, you twirl it, and everything that you want is possible. So if I hand over this magic wand to you, then what will you say twirl it for? And what, maybe if you want more specific direction to go in, what is the kind of research that you would like to do? Okay. Absolutely no ethical or financial issues.
Interesting. I think I kind of know what the answer is. I would try to sort of understand this quantum classical transition problem, and personally, I would try to understand how sort of we see the world around us, the world which is inherently quantum. So if I can get all the resources possible, and I don't have to worry about finances and ethics and so on, I would try to understand, like, just go full throttle into this direction and understand, and it encapsulates like a bigger thing, which is, I mean, it has the problem of quantum gravity in it, because quantum gravity, again, the term is, the quantum nature of gravity. We see gravity at this classical scale. How does it behave, in the quantum mechanical realm? And it's this parent term to understand all of this. And even like the current world without, not the current, I mean, the world that we actually have a better understanding as physicists, which is the world of, like the classical world that we see around us, Maxwell's equations and so on. So all of them have a quantum origin, and how all of this sort of transition, how does statistics emerge from something that is inherently quantum mechanical and so on. I would like to personally, like, this is on a research level, this, and on like a general level, I would say, and very very much related to, like, my passion for like being a part of this intellectual discourse in India. I think if I just get the wand, I would like try to get science into the mainstream pop culture as much as possible. So, for example, what COVID did to finance and stocks,
Right.
I would like to do that to science.
Right.
Because there's a lot of jargon and like a lot of like approaches that sort of keep science away from mainstream discussions.
Yeah.
So I want to sit in a bar with a mug of beer and be able to talk about science to folks, just like people talk about stocks and finances.
Yeah, I think, and it's also like a science bro, if there was
like a
one.
science bro.
Yeah.
Yeah.
But I think you are at a very unique position to be able to do that, because you are a communicator, you are
Right.
a gym bro, you're also like, like this scientist. And so, of course, you are at a very unique disposition to do exactly what you want to do.
So that's honestly all my science communication ventures, be it the podcast or just like, doing this with you, and
Yeah.
I try to I try to also like dabble into government affairs and policy, again, something that we can talk about later.
Yeah.
All of that, I think, is coming from a point that, I want to bring science back. No, I don't even know if it was part of like pop culture at certain point in history. But if let's say if it was, then I want to bring that time back. And if it wasn't, then I definitely want something like this to happen. Especially during this time in India, where it's like, with this booming economy, people are doing all sorts of things. Also, this previous guest, Ashmeet Singh, that I had a recorded an episode with.
He's a professor at IIT Kanpur.
Delhi,
IIT Delhi. Okay.
IIT Delhi.
Yeah.
So I'm from Delhi. He's a recent guy, a great guy to have on your podcast, by the way.
Oh.
Highly recommended. Reach out to him.
Great.
Fantastic guy.
Yeah.
Absolutely inspirational. I mean, I was just mesmerized. I was like, I don't want this episode to end like that level. So great guy. Also a great speaker. Everything nice. But anyway, so talking to him, I also sort of like felt the same. We sort of connected on this level. He also aspires for something like this to happen. He's senior to me, obviously. He's a professor. He's seen these changes happen in India over the past 10 years. So have I. And that's why I want to sort of like, this is like this, like you said, I believe I am this at this correct spot, the right spot in this big Venn diagram that I can sort of, bring back all of this mainstream, like science into mainstream. And that's when, people like it completely sort of, there's a phase transition of this intellectual discourse. People start talking about this. If people start talking about it, there's going to be more, money flowing into it, more money, more science.
Because good luck trying to moment. I mean, if you were to put a presentation in the sense that the way science is explained in generally, I mean,
right.
How, if for example, like you may know the greatest minds in your industry, but they may not be extroverts like you are, or they may not be like people who have communication skills. So good luck
Right.
sending them to Washington and trying to explain what you're doing and the relevance of it and whether it needs billions. Oh, by the way, I need billions of dollars for this. So yeah, so good luck
Correct.
convincing politicians and you superposition that on India and then
Even more
yeah, all the
complicated.
best. Good luck. Yeah, yeah. So what Doctor Sen said about not having any money for this, yeah. Good luck.
Right.
So we
So
need
yeah,
people
all of
like you
these
for
things.
like you're bridging this thing, right?
Right, absolutely, and it's been my dream, and becoming a great physicist, doing caring about the research project that I mentioned, all of
Yeah.
this quantum classical business, quantum chaos, something very dear to me, that and bringing back science to mainstream is sort of the two things that I really aspire for, and I am very passionate about both of them, and that's what dictates a lot of my daily activities. Let's just call it that. Yeah, yeah.
Well, thank you so much, Bhavya.
Of course.
This has been an education. I feel like I wish that I had met you at your age when I was in 11th. I think
Right.
you would have sparked my latent interest in science to the level where I would have also wanted to pursue it.
Appreciate that, man. Appreciate that. Honestly, that means a lot to me. And yeah, thanks for having me. I had a lot of fun.
Yeah,
Yeah.
please, if you have
Let's
any feedback, if you have anything to, I mean, if I can correct, I'll do everything I can to make things right.
No, of course, no, nothing. I mean, everything is fine. All is fine. You can all creative freedom to you. Just like go ahead and yeah. But keep doing this. I think this is good. You're thinking about this is actually I really respect this. It's missing from the podcast culture in India. Even I was extremely furious about this debate that just happened
Yeah.
on London Top about
Yeah.
does God
Javed Akhtar.
exist.
Yeah.
भाई scientists कहाँ हैं philosophers कहाँ हैं
Yeah.
have a big panel. I mean,
Yeah.
I'm not saying they shouldn't be there. They're experts in their own domain. It's fine. पर उनको आपने expert बना के वहाँ बिठा दिया. What the
Yeah,
hell?
yeah.
This is not fair. I mean, have people who have dedicated their careers to this.
To this, yeah.
वो वहाँ भाई मूवीज भी लिख रहा है, गाने भी लिख रहा है, इसके बारे में भी बात कर रहा है. ठीक है, it's fine. I mean, he's a public communicator, public figure, and you want to get him. I understand. You want your episode to sort of blow up.
Yeah, have millions. Yeah.
Yeah, but what the hell, man? Call philosophy. ऐसा नहीं है कि कमी है इंडिया में. There's I named so many Indians. Just give me I can send recommendations. Call him. Call that person, and so on. And have a debate, have an intellectual debate, and see where this goes. Get more perspectives. And even in the podcast culture in general, I have this complaint that people are not calling in experts. I'm not calling myself an expert, but there are
I'm calling you
experts
an
in
expert. Yeah.
Thanks. But even in science and so on, there's so many experts that can come and comment on the things that you're worried about. If you even let's say climate change.
Yeah.
But call a climate change expert and see if they expose them to science communication. Tabhi to intellectual discourse will flip. Otherwise, if you only have these known phrases and so on, and they're also talking about science and whatnot, rubbish stories, then there's no point. What are you doing? So I think this should change. Absolutely.
Thanks for saying
that. And I'm
that,
very conscious about that. Tabhi, I will bring in some IT professor.
Yeah.
Baat karo.
Exactly.
ठीक है?
I mean,
I
for
don't
me,
want to get
for me, these are unsung heroes. I've spoken to a mathematician, I've spoken to you now, I've spoken to a marine biologist, I've spoken to an archaeologist, a paleontologist, and you'd be surprised by how common these worlds, so many through lines exist in all these worlds.
Absolutely.
When you were talking to me, I was thinking, oh yeah, I remember this. My a senior of mine, Asim Sanyali, was a marine biologist. He is a marine biologist, and he was in these far off African islands for 10 years. He was on these islands and he was studying the endemic species there. And so much of his grievances with, say, advocacy and dealing with politicians is what you're talking about in this world, right? And there's so many through lines that I see because I've spoken to so many people, and I wish more people were engaging with these things and not
absolutely
listening
and
to
all these
ghost
communities
stories.
should come together. So instead of having these deep silos and not talking to each other. They should talk to each other.
Yeah.
And I think this is a great idea, and I think you're doing great. So
Thank you so much, man.
keep at it. Keep at it.
Thank you so much.
Absolutely.
If you learned something new from this episode of the Horsemouth podcast, do rate and review us on Spotify, Instagram, X, or wherever people engage with you the most.